What I should have mentioned at the beginning was some house rules, so I apologize for being a very, very bad chairperson for this session so far. What I should have said to you is that in case of any emergencies, if we have to leave the building, please follow the signs of the green man and do not use any elevators. Hopefully we will not have any problems. Secondly, everything that's spoken in this meeting is confidential, it's all amongst us, but because it's going out on the web anyway, please ignore what I've just said. Okay? So whatever you say is going to be used in evidence against you sometime. So, moving on. Jerome mentioned depth of focus. The funny thing is, with Goldstrand's original works on the optics of the eye, there was hardly any mention of depth of focus. And also, from the first speaker and from the second speaker, I've suddenly realized we've not had much involvement from scientists who predominantly spoke English in the 19th and 20th century. We've had Swedish, we've had Norwegian, French and Swiss. Now it's some time to mention the contribution of the English. And if we look at this first picture here, and this second one, this is George B. Airy. Is that name familiar to you? No? It will be in a moment. And here is a picture of a guy who became Lord Raleigh. Is the name familiar to you? No? It soon will be. Goldstrand, he put together his model eye, which we've got two simple representations of here. The simple model and the more complex model number 2. What George Airy and Raleigh did was what they used was diffraction theory. And what they showed was if you have an eyeball which creates a spot image of the retina, a spot, it is not a perfect spot, a perfect dot. The optical theory of diffraction shows that the light distribution of a dot, a spot at the retina, will have not a Gaussian distribution, but little bumps, rises, a big peak, and then other troughs and rises. These were due to diffraction theory. And the only way for the eye as an optical instrument to decide when one spot becomes two spots, when a spot becomes so big that it's no longer regarded as one spot but two, the two spots have to be separated by a set distance according to diffraction theory. And Lord Raleigh showed that you, as a person, will see one spot becoming two when your retinal image is such that the distribution of light overlapping the two spots hits a certain critical point. That was the Raleigh criterion. It tells you that you are not looking at one spot but two. Now, going on from that, there are certain things which the scientists from the 19th to early 20th century said were actually true, and there are certain things that they said which were not completely true. There is no 100% true and 100% false, but there are overlaps. And this is important because, according to Goldstrand's model eye, and according to the work of George Airy and Lord Raleigh, all of these optical prescriptions are different. Would you agree? If you look at these prescriptions, you all know what an optical prescription is. All of these prescriptions are different. But all of these prescriptions are the same prescription for a 37-year-old male patient who was refracted on the 22nd of June last year, almost a year ago, by 3 different optometrists on the same day. Okay? So, if Goldstrand's model was perfectly correct, and if the Raleigh criterion, the work of George Airy, was perfectly correct, why did these 3 optometrists get 3 different results for the same patient? Now, you could argue the patient wasn't very smart, wasn't very bright. Yes, this was a very bright patient. But this gives you an idea of how much you and this 37-year-old patient could tolerate. Most of us, as clinicians or scientists, think that we can walk or even run on water. You can't. The margin of error when you refract somebody is of the order plus or minus 0.34 to plus or minus half a diopter. How do we know this? We know this simply from clinical studies by these individuals noted here. And this phrase at the bottom is important. Some of you may recognize this phrase. I know one person certainly knows what this phrase means. Nullius convergere. In round terms, don't take anybody's word for it. If you don't believe the figures that you see from this presentation and others later today, then find out for yourself. These are the errors of simple refraction. The optics of the eye is such that these kind of errors of refraction should not be tolerated. But the human eyeball is inside a head with a brain. And that is where the errors start. This is why we have this range of tolerance. Now, if we have a range of tolerance, perhaps we have a range that the eye can tolerate an image as remaining clear. The depth of focus mustn't be confused with depth of field. The depth of focus, as I'm going to point out in this diagram here, is the range the retinal image can be in focus and out of focus, but tolerated by the human eye. The depth of field is this range translated into real space. The eyeball as an object, as a perfect optical device, as a perfect optical device, should only can only resolve 2 dots on the retina separated by between 0.003 millimeters and 0.004 millimeters. These figures here, published in the 50s up to 2000, these shows what is the range of tolerance of an image on the retina. And these tolerances are on par with the size of a corneal, of a retinal cone. Okay? So, in theory, the eyeball is a fantastic optical device which can tolerate very, very little. But in reality, we know that the real depth of focus of the eye is much higher than pure physics tells us. Why is that? The reason why is that as you are looking at this screen and then taking some notes if you wish, You think your eyes are perfectly still. You think your eyes are remaining still. If you looked at my finger, as far as you are concerned, your eyes are remaining perfectly still. No, they're not. Your eyes are constantly moving. There is a constant, irregular, this tremor, this flicks, and this drifts. Some of you might even be drifting into sleep, but there are still drifts. Okay? Now, because of these irregular movements and tremors of your eyeballs, the retinal image is also moving. But you are not aware of your retinal image moving. Why? Because you're cool, calm, and collected. But your retinal image is moving. Now, at the same time, your eyes are blinking every so many seconds. When you are reading, you are blinking round about once every 15 seconds. You are concentrating. When you are walking around, when you're talking to each other, right, you are blinking much more than once every 15 seconds. You are blinking around about once every 5-10 seconds. No, you're blinking once every 4-5 seconds. Okay? What this means is that your retinal image is moving, it is becoming blurred, but you do not know that it's doing that. Because your consciousness phases that out. What this means is that the retinal image could change by up to 0.1 millimeters and you won't even know. Unless you concentrate, you do not know if your retinal image is made more blurred by up to 0.01 millimeters. So, what does that mean? It means that your depth of field is much bigger than you think it is. Jerome talked about accommodation. The eye, as time goes on, your lens becomes stiffer. But at the same time, as you are looking, you believe your retinal image is steady, but your lens is doing this. There are micro fluctuations occurring all the time, and they are in tune to your heartbeat. And because John Marshall had 2 cups of Portuguese coffee this morning, his heartbeat's going like this. So his micro fluctuations are going so fast that we can't keep up with them. That's why John is so laid back and calm. Because he's completely unaware that his lens is shaking, and he's completely unaware that his retinal image is moving because his brain is remaining cool, calm, and collected. So, your depth of focus will actually depend on your pupil, how far away your object is that you're looking at, and the movements of the eye. The depth of focus in relation to the size of the pupil. This is some recent data that we've collected with Kleist. If we measure your depth of focus, your depth of field, when you're looking into the distance, as your pupil becomes smaller, your measured depth of field at a normal pupil size of 4 millimeters is around about 1 to 1.5 diopters. In other words, you can tolerate quite comfortably an object from infinity brought up to almost a meter away from you, and you will still accept it as being relatively clear. As your pupil becomes smaller, your depth of field will increase. So you can have, if you're lucky, up to 4 diopters of depth of field if your pupil was made 2 millimeters smaller. What this slide shows is that if we artificially make your pupil smaller, the change in your depth of field is directly linked, correlated with the change in the size of your pupil. So what we can do is remain very, very calm and collected. Very calm and collected. Your natural crystalline lens has become stiff, but if you remain calm and collected, you can unstiffen yourself very easily. Now this is the way you should relax. You remain calm and collected. But you can also do this in Northern Europe. It's very easy to do in Northern Europe using other types of stimulants. Clear point I'm trying to make is that because we can tolerate a range of depth of focus, we can now go beyond Goldstrand's model line. And I did this with John Marshall years ago. We produced an aspheric model line where each surface within the eye was aspheric, and it included what's called gradient index optics. We went a little bit further. We published on it, as I said, in 1998, or earlier than that. Using our model line, knowing how much of the depth of focus the eye can tolerate, how much could we make in terms of putting in an artificial type of implant lens, either bispherical, aspherical design into an eyeball, how much of a depth of focus could we possibly achieve? Well, this slide summarizes our calculations where it's possible using a multifocal aspheric implant lens or an add-on implant, which is a dual optic system. We could create depth of focus increases by up to between 1.5 and 2 diopters. That isn't bad if we accept that the eye and the brain can be fooled into accepting an implant lens which will improve the depth of focus, which is what I showed you earlier. So, how can we improve the depth of focus? Not too difficult, as long as we are careful in the way we select patients. Patients with small pupils, a bi-lens system like an add-on, and optimize the aspherics, we have a good chance of increasing the depth of field for this eye after surgery compared to before. The patients or the eye that is not going to do well is the eye that's got a big pupil that has a monofocal IOL, which has an insufficient asphericity. That isn't going to work. By sticking to this simple 3-part system, we've got a good chance of improving depth of focus and therefore correcting vision in post-cataract and possibly pre-cataractous patients too. So, I think I've given you a slightly different perspective of how to look at this problem in a slightly different way by controlling depth of focus. And are we going to manage to achieve this? Well, yes. Because what we are doing now is something which I must thank AWA for. Because AWA allowed me, Klaus, and Magdaram to look at the forbidden books. The forbidden books are the goal that we want to achieve. That is a way of correcting the age-old problem of presbyopia, because human population is aging, our life expectancy is higher, and we are now tapping into things in terms of science and research which were one time regarded as taboo, just like the forbidden books. Thank you very much for your attention.